I have a question here. Why some materials have distinct magnetic properties, while some materials have not? We know the magnetic field is produced by a current. In other words, the current is the source of a magnetic field. Therefore, to answer this question, we must find the origin of a current at an atomic level, leading to the magnetic effects of the materials. Based on the classical model of an atom, electrons are moving in a circular orbit around the nucleus. We know a current is a net flow of the electric charges. Therefore, a moving electron actually creates a circular current. Now let's define the equivalent current associated with this orbiting electron. We assume an electron is a particle in a uniform circular motion. It moves with a constant speed v in a circular orbit of radius r about the nucleus. By applying the definition of the current, the rate of the flow of the charge through some region of space, it can be expressed by a mathematical equation. I equals the derivative of q with respect to t. That means the charge is passing through some surface per unit time. Hence, the current I associated with this orbiting electron is its charge E divided by its period. The period is equal to the circumference of the orbit divided by the speed. Thus, we have this one for the current I associated with the orbiting electron around the nucleus. Therefore, we can have the magnetic dipole moment, which is associated with this equivalent current due to the orbiting electron. Please recall, how about the magnetic field produced by a circular loop carrying a current I? For any current loop, we define a magnetic dipole moment, mu. Mu equals IA, where A is a vector. The vector A is perpendicular to the plane of the loop and has a magnitude equal to the area of the loop. The magnetic field on the central axis has the same direction as the magnetic moment dipole, which is determined by the right-hand rule. Thus, the magnitude of the magnetic moment associated with this current loop is yielded by substituting I and A. Because the magnitude of the orbital angular momentum of the electron is given by this one, L equals mvr, the magnetic moment can be rewritten as this one in terms of the angular momentum. This result demonstrates that the magnetic dipole moment of the electron is proportional to its orbital angular momentum. Because the electron is negatively charged, the dipole moment vector and angular momentum point in opposite directions. Both vectors are perpendicular to the plane of the orbit as shown in the figure. But we have not answered the question yet. All materials contain electrons, but why most materials are not magnetic materials? Actually, in most materials, the magnetic moment of one electron in the atom is cancelled by that of another electron which is orbiting in the opposite direction. As a result, for most materials, the net magnetic effect caused by the orbital motion of the electrons is either zero or very small. However, in the atom, in addition to the magnetic moment associated with the orbital motion, an electron as well as protons, neutrons, and other particles has an intrinsic property which we call spin. Spin could contribute to the magnetic moment of an atom. From the classical view, an electron could be modeled as a particle which is spinning about its axis as shown in the figure. The magnitude of the angular momentum S due to the spin of an electron is predicted by quantum theory, where h bar is Planck's constant, and the spin angular momentum S is on the same order of magnitude as that of the orbital angular momentum L. The magnetic dipole moment associated with the spin of an electron equals this one. We call it the Bohr magneton. So, the magnetic dipole moments can be expressed as multiplies of the Bohr magneton. An atom contains many electrons, which pair up with their spins of opposite directions. Therefore, the spin magnetic moments cancel each other. Then, how about atoms containing an odd number of electrons? They must have one unpaired electron so that the net magnetic moment of spin will not be zero. Hence, the total magnetic moment of an atom should be the vector sum of the orbital magnetic moment and the spin magnetic moment. Here, please note that the magnetic moments of a proton and a neutron are much smaller than that of the electron and could be neglected. Please think about why. So, in this lecture, we explored the origin of the magnetic effect of a material from an atomic level. In the next lecture, we'll explore the average field produced by the dipole moments all aligned.